Good morning, everybody, and I hope everybody is well rested. So I'm Sujit Sinha. I'm working for IIT Delhi. So today I will be talking about some of my experiences with soft Materials-Tribology, and as Professor Kim told you that I have been working in the polymeric field for quite some time. And this polymer field is quite related to orthopaedic applications, implant applications. So I will be sharing some of my observations and some of my results, as well as some of other researchers' results to bring together how we deal with soft metals when it comes to tribology. First of all, since it is related to our joints, orthopedic joints, our body joints are under much more stress than before. Okay. So perhaps people in the olden days also had this kind of stress, body stress, but they had different kind of stress. Today we are giving different type of stress to our body, so that might be working against us. But it is true that we are giving a lot of stress to our body, I mean the mechanical stress. And there are also things like injury or aging can also lead to some problem, can lead to joint wearing out or osteolysis. Osteolysis is basically an issue where the joints, cartilage of the joints degrade. And obviously the cartilage is the best tribological pair. You can imagine. They work day and night with very low friction, low wear, but there are some problems. And I would like to share this picture of Professor Yoshiro Azuma, who retired at Sophia University of Japan, and now he is working in India. He was my colleague at IIT Delhi for 4-5 years, all during the COVID. He was there, and then now he has moved to Birla Institute of Technology, Goa. He is 70 years old, and he is still biking. He is not going to, sell his bike, so he is still biking. So you can see that he is a professor in physics department. So, osteoarthritis is a big serious problem, and not only for older generation, but also for younger people who face issues because of trauma or work-related cases, or sometimes just overuse. And this basically leads to loss of articular cartilage. So the cartilage which takes the load of the joints are called articular cartilage. So these kinds of cartilage are exposed to various types of trauma and injuries, and that can lead to the osteoarthritis, including the age factor. So this problem is serious for hip and knee joints. So we focus on hip and knee joints because, as you know, our hip and knee joints take all the load of the body, and there is no alternative. The body has to use these joints for taking the load, and the quality of life basically depends on these joints. So the body weight is completely borne by these joints. So the load is quite high, and at this kind of load, how can the cartilage will work? Basically, it is a ball and socket kind of arrangement for hip joint, and the load is very, very hard, and under this kind of loading, the joints have to work. Okay. Of course, it's always good to have the natural joints, but those who for some reason may not be able to continue with the natural joints, then they have to go for surgery or implant. So this picture shows how the implant, the main parts of the implant, and so this has got the acetabular component, and then there is a plastic liner, and there is a femoral head which is on the thigh bone. And these two interact in this way. So this is the combination. after implant. So this combination works just like a normal bearing you can think of. So the sliding takes place between the metal part, which is covered chrome molybdenum, and the plastic part. The plastic is fully attached to this part of the implant. So the sliding happens between the two. Of course, there is a synovial fluid which works as a lubricant between them. So this synovial fluid is supplied by our body itself. This shows another example of the knee. Both have got very similar problems, similar issues, but the contact geometries are slightly different. In fact, knee might be more serious in terms of because the contact is not non-conform. Looking at the structure of our cartilage, first we should understand how the cartilage works. Only then we will be able to perhaps design a new material. So the cartilage is basically a hierarchical structure, okay, and the top structure is called extracellular matrix. So this matrix contains many things inside. So for example, collagen fibers. There are different types of collagen fibers, enzymes, glycoprotein, and hydroxyapatite. They all provide structural strength to the cartilage, because this material also must have good structural strength. And then you have proteoglycans, the lubricating parts, which are also embedded within this ECM. So the proteoglycans provide lubricating properties. So this is an extremely complex structure. This is not at all what we can imagine as cartilage as one material. This consists of many macromolecules. Looking a little bit more, the synovial joints, it has got proteoglycans. So these names will keep appearing. For example, hyaluronic acid, leucine, aggregans. These are all molecules, macromolecules, which are present in the ECM as well as in the lubricant itself. And they mainly provide the lubrication properties. And if you section the cartilage, then basically you see these kind of things. So this side is the bone, it is attached to the bone. This is the articular surface, this is the top surface. And you can see that even the mechanical property change with depth. So for example, here it is very soft. As it comes closer to the bone, it gets stronger. So this is a very beautiful design of the nature, how the cartilage works. That means it has got sufficient strength where the strength is needed. At the same time, it provides a good lubricating properties. On the top surface, if you see, this is the schematic drawn, which is shown here in the bigger schematic. So structure of the cartilage, boundary lubricant layer. So it has got collagen network. Collagen network works as a structural component. It provides sufficient strength. Lubricant molecules, HA, phospholipids, and there are many charged particles, charged macromolecules. So these charged macromolecules basically act to attract water molecules, because as you know, nature works with water as a lubricant, not oil. So the water molecules have to be attracted to these surfaces. So basically they act as a site where the water molecules can attach themselves with and provide lubrication. Looking further, proteoglycan molecules, they look something like a bottle brush, where you have got the main link here, which is protein, and there are side brushes here. And these are different molecules, for example, chondroitin sulfate, keratin sulfate, and so on. These are all charged macromolecules, so they are charged at certain points. For example, here COO, and they provide as a attraction site for water molecules, and that is how the lubrication works. So we can understand cartilage as a very, very complex living thing. And another important thing about cartilage is that there is no blood supply. Okay. So what it means is that the cartilage cannot repair themselves, by themselves. And that is a big problem. So basically, we have chondrocytes, molecules which act as a repair cells. They go and they repair the cells, but there is no blood supply. So that's why any damage done to the cartilage can lead to permanent damage, unless it is solved by some other means. The body generally will ignore it. So looking more into the implants. So acetabular cuff, and this, the liner material is UHMWPE, ultra high molecular weight polyethylene. So this is currently is a standard material. This is used, and the femoral head has been used, metal, ceramics, and so on. There's another thing about the artificial implants is range of motion of the femoral head. So how much motion can we get? So the nature's designed joints, as you can see, that if we range of motion can be very, very high. Okay. So this is the range of motion, but the implant range of motion is not that much. And if you want to keep the motion range of motion high, this thickness of the liner must be small. A very thick will obstruct the motion of the femoral head. So the thickness of the liner should not be too much, which tells us in terms of mechanical strength that the mechanical strength of this liner must be high, otherwise it cannot take the load. So as I said, UHMWP has been a polymer of choice since 1960s when Charlie used. There have been many developments in this field. For example, cross-linked UHMWP have shown better mechanical properties and better wear and fatigue properties, but they have oxidation degradation, and that might obstruct the wear properties themselves, wear and fatigue properties. So vitamin E has been used as an additive for cross-linked UHMWP, and vitamin E actually is an antioxidant, and therefore it helps to prolong the life of this material UHMWP. That means it avoids the oxidation. This is an example of the retrieved implant from the knee, and it clearly shows the adhesive wear, oxidation wear, and fatigue wear. You can see there are a lot of broken parts here. A lot of wear has taken place. So even though the material is good, the lubrication is good, but it's still they wear, and that's because the lubrication regime is boundary lubrication or mixed lubrication. So in the boundary and mixed lubrication, we know that the wear will take place. So UHMWP has been a good choice so far, but there has been a lot of research and a lot of development in the materials, and I will share some of my results as well as some other researchers' results. So two new materials have been tried. One is epoxy-based, another is hydrogen. The epoxy-based, maybe you have not heard so much. So we have started working on a material called Structlite. This is epoxy, and this is basically a dental material. So they use for dental implant or dental repair. And if we add UHMWP composite particles and make a composite out of it, they at least in the laboratory test they show very good results. Another is hydrogels. Hydrogels are very, very popular these days. In the last just couple of years, we have seen so much of research happening in hydrogel. So hydrogel is basically a polymer which absorbs a lot of water molecules. Okay? So, for example, if you have tried the bubble tea, so the bubble inside the bubble tea is actually hydrogel, but this is a natural hydrogel. So the natural hydrogel is very good in terms of biocompatibility with us, but in terms of mechanical and tribological properties, they are not good. So therefore, we have to go for synthetic. This group compares one small particle hydrogel, which is dry, and after soaking in water, it expands so much. So almost like 80% water volume by volume you can have in the hydrogel. So obviously, water is used for lubrication. So I will present some of the challenges, and I think the speakers yesterday also talked about big challenges for soft contacts. So first is the contact area. The contact area, how to control the contact area. So if we are going for very soft material, obviously contact area is going to increase. If we are going for harder material, the contact area will reduce, but that might want some other issues. Then surface adhesion or repulsion. Surface adhesion is also very much closely related to the contact area, okay, as well as surface energy, the type of molecule we have, then the shear properties of the interface. At the interface, what happens? Okay, what is the shear property? So that is another important issue, and shear properties will depend upon the speed, how fast we are moving or sliding, because especially for younger generation, they might be more active than older generation. So you might have to think about the shear rate issue. Another is local roughness. Roughness is also remains a big issue, even for implants where the surface roughness is reduced as much as possible. But still, if we are going for a little harder material, then surface roughness will be important. So these are the main four, I think, issues which are important, and I will just go through them. For example, contact area, we know that Gaussian contact Gaussian equation can be used for finding out the contact area, and especially for softer contact, we should use ZKR model rather than Gaussian contact model. So this is the ZKR equation. Here, the only difference is that surface energy has become an important part of this. Okay? And if you consider that there is no effect of surface energy, that means there is no adhesion effect, then the JKR model basically becomes the same as Gaussian model, which is given here. Now at separation, when you are bringing the two surfaces apart, the external force experienced or the adhesion force will be given by this one. So here you can see the R is the geometry, the radius, and gamma is the interfacial surface energy. So surface energy plays a very, very important role in adhesion. And when we are talking about boundary lubrication, where we have the possibility of dry contact, this adhesion will be an important part. This equation for the adhesion force is same as Bradley's equation, which was given long back, which also relates to the surface energy. This basically says, in terms of graph, you can see when you are separating the two surfaces apart, say a ball on a flat plate, and the joining force, you are reducing the joining force as the contact area is decreasing. For Gaussian contact, it will come up to 0 and then it will separate, okay, because there is no adhesion. But for JKR model or for softer contacts, you will have some finite contact area even at zero load. So that means you have to go for the negative load and then bring the separation. So that is called pull-up force. This graph has been nicely compared by using these non-dimensional numbers by Karpik and Salmeron. So where you can see the Gaussian contact, there is another model which is DMT and the JKR. So the contact problem immediately leads to surface adhesion. And many people have done work on hydrogel. So this is work on hydrogel, and there is a huge amount of adhesion. This is the indentation and reverse loading and unloading, and you can see that energy of separation is quite large. Then the pull-up force is something which depends upon so many other factors. For example, contact time, how long it has been in contact. It's almost same as, we experience some pain in the joint if we sit in one position for a long time. So this is a time problem, time issues. Okay, as well as how much depth, that means how much load we have applied to the contact, and the pull-up force will be different. So these are all experimentally observed data. Then the shear properties. So shear properties, basically, as yesterday Bizan was talking about, tau is equal to tau naught plus alpha p. It's a pressure dependent. That means the shear stress depends on the pressure also. And very first data were shown by Briscoe and Evans on steric acid. So this is the relation, the same relation as we saw yesterday. And in our work, we have done work on UHMWP sliding against a silicon nitride ceramic wall, and we find that the same type of relation, shear stress as a function of pressure, but it does depend upon the adhesive force, that means the surface energy. So as we change the surface energy, it is changing. For higher surface energy, the term of which is the intercept is increasing. So it is dependent upon surface energy. And further we model this one. So initial shear stress as a function of attractive force. And here you can see a logarithmic equation here, exponential equation. So that means the initial shear stress, which is tau naught, depends upon the attractive force in a exponential manner. And further we actually developed, and we found that the coefficient of friction can be actually related to the pull-up force. So this using the pull-up force, experimentally we calculated pull-up force, and we have related this mu to the pull-up force with some constants here. And you can see that they fit very well. And these are done for high surface energy as well as for the low surface energy cases. Another is surface roughness. So we are quite aware of surface roughness issue. So as you increase the surface roughness, the pull-up force will go down. That means adhesion is less. And that's why nowadays some people are trying texturing on the implant so that we can reduce the adhesion force. So, and as well as the pull-up force depends on the modulus of the material. So this is increasing the modulus. I'll show you some data on the hydrogel and the epoxy composites. So basically, you can model the hydrogels as normal octane elastic material, but in true sense they are viscoelastic materials. So, for example, different types of composites have been made, and goes to the natural cartilage, as well as the wear depth in terms of tribology. Some of the composites where this one PC, PVA, PA, and PS, this composite has given even better in terms of wear resistance compared to cartilage. So by making this kind of composites, you can actually improve their tribological properties as well as the strength property. PVA is a very popular material, and this is quite old work now. So different way of making hydrogel can also have some effect. So here cast, drying, and freeze and thaws method were used, and you can get better result by the combination of these. And this shows how the wear surfaces look like in the previous video. Another development has been on the Zwitterian polymers. Zwitterian polymers are basically in macromolecules which has got both the negative charge as well as the positive charge. So overall they are neutral, but they have separate negative and positive charge, so they can act as a water holding places. So they are very, very effective. And for example, average coefficient of friction can reduce if you increase this deuterium molecule inside another molecule, for example in PVA, and about 10% can do a very good job for this. Similar idea has been used here as well, where deuterium polymer has been added to some other polymers and hydrogel has been made, and you can see that the mechanical strength, by making some composites, mechanical strength can be close to the cartilage, but not yet, and the friction property is quite good even compared to cartilage. So by doing this kind of innovation, it is possible to improve upon the artificial material for implant application. This is from our work where we have used Structline and UHMWP particles, as well as HA, which is hyaluronic acid, which acts as a lubricant. So this combination, and this shows how the particles look like. They are very, very strongly attached to the matrix. And we conducted this test in a rotation and sliding continuously, which so this is the machine where the pin is actually rotating on its own axis, as well as it is sliding linearly. So some Vickers hardness tests we compared with UHMWP. So they have better results, better mechanical strength, and in terms of coefficient of friction, they can be slightly better than normal UHMWP. So they have a lot of potential, and as well as specific wear rate is also low. Of course, these kind of tests are quite complicated, but we have been able to get some initial results on these. This one is with HA, hyaluronic acid, and you can see the coefficient of friction is quite comparable to UHMWP, and the wear is very, very low. In fact, in some cases, you may not be able to even measure the wear. And looking at the microstructure, we have seen that the particles, the UHMWP particles are intact inside. They are not something which will come out of the matrix, so that is good. So I come back to my colleague Yoshiro Azuma. So he has been biking, walking very well, and you can see his right leg, and he showed me the X-ray of his right leg, and this is actually he has some loss of cartilage, which he indicated, and then he got the surgery done on his knee. You can see there. So this is his right knee. This is just after recovery. He had recovered from the knee, and right now he is biking. He's still biking. So he is very, very good. So he told me to pass on the message that he wants to visit Samarkand very soon. So very soon you will see him biking here in the campus. So let me just conclude. It is important to continuously design and experiment new materials for hip and knee implants, various types of composites. The effects of parameters such as contact areas, adhesion, interfacial shear properties, local roughness on wear and friction are to be understood at a very scientific level. And the soft materials with sufficient mechanical strength and lubricity are needed for acetabular design. So we need both mechanical strength as well as the good tribology. So thank you very much for your attention.
Almost not. The tribology of the stem cells.
Yes.
One more question, and then I have to read if we need to move on. Yes.
Very interesting talk. So thanks. I have a question. In one of your last slides, you showed that all the wear particles are embedded into the composite. Is that right? Yeah. That's
Okay. Yeah.
Yes. Here. So these are the wear particles that is kind of.
No, these are not wear particles. These are the UHMWP particles that have been used as a strengthening mechanism.
I see. Okay, so, thank you.
Okay, the question is short.
Yeah, actually, you have shown the influence of surface energy on friction. How it means that you calculated, what do you mean? Is this that you calculated the breakage of van der Waals bonds, or? Okay.
Yeah, you just please repeat.
Actually, okay, you showed us one slide where you said that you calculated the influence of surface energy on friction.
Yeah.
And actually, surface energy, in this sense, I believe it is work of adhesion. Okay, twice. So how did you calculate it?
So we calculated a pull-up force by measuring the water contact angle and surface energy. So we measured the surface energy of the interface, and that is how we got the pull-up force.
And the influence of friction?
This shows the initial friction, that means before the wear took place. Very, very beginning of the only friction.
I think we have to move on because of the schedule. Thank you very much. Sujit?
Yeah.